Students, we will discuss the continuation of the previous topic. That is, till now we have discussed the power spectral density of a weakly stationary random process, and now we will discuss about the properties. So the first property is zero correlation among the frequency components. It means that the individual frequency component of the power spectral density, that is Sxx of f of a weakly stationary process, is uncorrelated with each other. So this is the illustration of the power spectral density. So our power spectral density is denoted like this. Here we have two narrow bands, right? So this small portion is represented as del f. You can see that this is another band. This is another frequency band, but there is no correlation between these two adjacent bands. So this is the first property, that is, there is no correlation with each other. So each individual frequency components are uncorrelated with each other. This is the first property. Second property is zero frequency value of the power spectral density. So we have the equation. In that, if you substitute, if we have the Wiener-Kirchner relations, right? So take this first expression. So in this, substitute f is equal to 0. So this term exponential becomes exponential of 0. Exponential of 0 means it is 1. So we will have x of 0 equal to integral minus infinity to infinity, or x of tau into d tau. So this is what represented here. So take your equation number 1, xx of f equation, that is first equation in Wiener-Kirchner, and substitute f equal to 0, you will get this. So the zero frequency value of your power spectral density is nothing but it is equal to the total area under the graph of your autocorrelation function. So that is the second property. Third property is mean square value of your input random process x of t. So this is nothing but the total area under the power spectral density. So it means that it takes the total area. Total area means integration over all the frequencies, and then power spectral density of the random process. So this is df. So this gives you the this property, next property. So you can take your equation 4.43. This is from your this equation. We are taking this equation and processing, and we are getting the third property. So mean square value of the stationary process. So if you use the same condition there, we will have rxx of tau, right? So that substitute 0 and it will be equal to your expectation of x square of t. Next one is fourth property is non-negative of the power spectral density. It means that power spectral density is always positive. You will not have any negative value. So how you can represent this? Xx of f is always greater than or equal to 0 for all frequencies. So this is the fourth property. And the fifth property is it is symmetry. In first property itself, we have discussed how we have plotted our power spectral density Sx of f. It is bell shaped, right? So whatever you are having in your positive axis, you will have the same in the negative axis also. The graph is similar, right? So you can write as whatever is available in positive frequencies, you will have the same in the negative frequency. So how you can denote this? It is nothing but symmetry property. It is an even function of frequency. It means that your xx of minus f is equal to sxx of plus f. So this is your symmetry property. And the final property is normalization. So power spectral density has the properties associated with the probability density function in your probability theory. So you can get the spectral distribution function as per this formula, fxx of f equal to integral minus infinity to f pxx of v into dv. So this has the following properties. Substitute f is equal to minus infinity, you will get it to be 0. If you substitute plus infinity, you will get it to be 1. So this is a non-decreasing function of the frequency. So these are the 6 properties of the past spectral density. So first one, we will have a look, that is zero correlation among the frequency components. Adjacent frequencies won't have any relation between each other. All the individual frequency components are uncorrelated with each other. Second property is that your zero frequency value of the past spectral density is nothing but area under the autocorrelation function. Third property is your expectation of mean square value of the random process is nothing but area under the power spectral density. Fourth is it is always positive. Your power spectral density is always positive. Fifth property is it is symmetry. So whatever you have on your positive axis, the same thing you will have in your negative axis also. And the final property is normalization. So these are the properties of power spectral density. Thank you.